Hello, good evening, everyone. Am I audible to everyone? Hi, good evening, good evening, good evening. So, again, welcome everyone. Welcome to our channel. And today I am here with one of very interesting topic, and that is on how actually aircraft engines are designed. So, guys, I welcome you all to my channel, and over here we discuss a lot of amazing thing. And today I am going to share my knowledge on how the aircraft engines are actually designed. Okay, guys, today's session is going to be very interesting. Those of you who have keen interest in aircrafts or aerospace engineering, or if you want to learn about aircraft engine designs, then you are at the right place. And keep watching this video for full, because today I'm going to tell you how actual aircraft engines are designed. Okay, before moving on, guys, those of you who have not subscribed to our channel, hit the subscription button, which you are seeing over there below our video. So subscribe to the channel, as I'm going to bring a lot of interesting videos, a lot of stuff which is interesting, like this lecture only. Okay, guys, in case if you have any doubt, or if you have any comment, you can write it in the comment box. I will try to reply you all as much as possible. Those of you who are not watching this live also, guys, if in future if you have any query or any comment, you can write in the comment box, and I will try to reply to that. Guys, as I am telling you this, probably I will not be able to take a lot of questions from those of you who are live. So I will wait for the full lecture to finish, and then after that I will reply to all your comments. So stay tuned, guys. I'm going to take all of your comments and wait for some time, because I know that there are going to be a lot of questions from you all, and I'm going to answer all of them. Okay, so hold on, guys, watch this complete lecture, complete video, and then we can discuss about your doubts. Okay, so guys, let's start today's lecture, which is on how to design, or how actually aircraft engines are designed. Okay, to start with our lecture, guys, I want to give you a brief about what the actual aircrafts are. I'm sure you guys might be knowing what the aircrafts are. So aircrafts are generally the machines or vehicles which are used for transportation of cargo and humans from one place to another. Okay, the specific thing or the good thing about the aircraft is you can move transcontinents, you can fly from one place to another place, and that too in the shortest possible time. Okay, we have these aircrafts which move at very high speed, roughly in the range of around 700 to 800, around 900 kilometers per hour. These are some of the aircrafts which are used for general aviation purpose. We have other aircrafts also, we have rockets, we have fighters, which have some other different purpose. So I'm sure, guys, a lot of you might be having an idea about what an aircraft is and what are the different types of aircraft. So if you see on your screen, this is one of the largest aircraft that we have. This is aircraft A380. This is used for transportation of people from one place to another place. There are other transport aircrafts which are used in the civil aviation, like this as well. Okay, if we move on to other categories of aircraft which are there, if you see here, we have two other type of aircraft. One is this aircraft, which is actually a fighter aircraft that is used for military purposes. These engines, they also have similar engines to like aviation aircrafts. These engines, they have mostly all of these engines which are used in the aircraft, they primarily are somewhere the derivatives of gas turbines. Gas turbines run on Brayton cycle. Okay, so this is one of the aircraft that uses a jet engine. Okay, Similarly, on the left and on the right hand side, if you see on the bottom, we see another aircraft that is actually a space shuttle used to go from Earth to space and then come back from the space. This takes astronaut to the space and then bring them back to the Earth. They also have an engine which is similar to the jet engines. That is probably, you might have heard the name, and that is the rocket engine. Okay, these aircrafts are assisted by other rockets to take this aircraft to the space, and then while coming down, these enter into the atmosphere, and then they behave as a normal aircraft while while they are landing. So these are some of the types of aircraft that we actually have, or that we actually see nowadays. Okay. Now let's go to the next section, which is why the aircraft engines are required. If you have an aircraft, what is the need of an engine, and how we actually design these engines, or what are the different components. Okay, so first we are going to see very basic about why the aircraft needs an engine. Okay, so to understand this, let's take a very simple example. Let's say you have a boat which is a paper boat. Okay, I'm sure all of you might have played with this boat when you were childs or children, when you were young. Okay, so if you have a paper boat and if you make it place, or if you place it on water, what you will see? You will see that when the water is still, and if you are placing a boat, that will stay at that same location. Now if you want to make this boat to move forward, if you want this boat to move forward, what generally you do? You generally push your boat from the behind. Let's say you have your hand over here, and then you push this boat. The moment you push this boat moves further. Okay, so this is a simple example that probably you might have done it. Okay, so whenever we want to propel this boat front in the water, what you do? You actually apply some force from the behind. I'm sure you all are engineering students, and you must be having little knowledge about the force. Okay, so generally you need some force to move some things further. Okay, this can also be understood by, let's say there is still water and you put your hand inside the water. Now if you want to move your hand front, okay, or if you want to move your hand in this direction, what will you do? You have to apply some force on your hand. Okay, so generally to move things through a fluid, generally we need some force. Okay, I'm sure you must have got some idea about the force. So if there is an object that has to be moved through the water, or it has to be moved through some other fluid, you have to apply some force on that object. Okay, the same principle is used to propel your aircrafts also. Let's say you have water. Also take an example. Let's say you have a water. In that water there is a fish which is standing at one location. Now if the fish has to move through the water, if you want to move, or if this fish wants to go forward, what will it do? What will it do? It will try to push or propel itself through the water by movement of its tail. Okay, this is the tail that is moving. So that when that tail is moving, actually that tail is pushing some water behind. Okay, some water is pushed behind, and in that process some thrust is exerted on this fish so that it moves in front. Okay, so whenever a fish is moving, it throws some water behind, and in turn it is getting some thrust, and because of that thrust it is moving forward. The same principle happens with your aircraft as well. Okay, so if you see an aircraft, let's say we have an aircraft, simple aircraft. This simple aircraft is nothing but it's again an object, okay, that is moving through one of the fluids. Okay, so you have air which is throughout. You have air which is present throughout your space. Now your aircraft is moving forward. When aircraft is moving, aircraft is nothing but what? It's an object. If it is moving, it is going to move through the space or through the atmosphere. It needs to be applied on with some force. that force is nothing but the thrust. Okay, why this thrust is required? Because when the object will be moving through the fluid, there will be some frictional drag which will be acting on your aircraft. Okay, so there will be frictional drag which is acted by air on your aircraft. To overcome this drag, we need some force so that your aircraft can move forward. Okay, so this is the basic principle of how an aircraft actually moves in front. You apply some thrust on this object, this plane, and it will move forward. This thrust would be used to overcome the frictional drag which is acting on your aircraft. Okay, so guys, this is very simple principle. Okay, so now if you want to understand that what is the purpose of an engine, why an aircraft needs an engine, because engine is that device which is actually used to produce the thrust. Okay, so engine, if you see, these are the engines. If you have seen any of the aircraft, these are the engines which are actually placed on an aircraft. This is an aircraft A380 which has got four engines, two on this wing and two on the other wing. Okay, so these are the four aircraft engines which are there. These engines would actually generate a thrust which is going to propel your aircraft. Now, this how thrust is generated, how engines generate thrust. To understand a simple concept of thrust, how actually the thrust is generated, probably you might have heard Newton's third law. Every action is equal and opposite reaction. So the same principle is used by your aircraft engine as well. So we have your engine. Let's say this is one of the engines that you have. This engine, what it is going to do is, it is going to take in some air from the front. It is going to draw in some air from the front. This is going to draw in air inside itself, and it is going to throw that air with high velocity. Okay, so it is going to throw it with high velocity. I'm sure you might be aware about the Newton's second law and Newton's third law. Okay, so whatever is the thrust, the value of thrust that is generated, value is 50 kilonewton, 100 kilonewton, whatever is the value, that is decided by Newton's second law, and the principle of action and reaction is decided by Newton's third law. Okay, so the air which is having very less velocity, u of roughly around 0, that is moved or accelerated while passing through the engine to some very high velocity v. So when this air is getting outside, when this air is getting pushed towards behind, there was some force which was used, or there was some force which was applied on this air so that it starts moving backward. That same force was applied by your aircraft engine, and since the air was applied with some force, this air in turn is going to apply the same force in the forward direction to your engine. Okay, so this is how your thrust is actually generated. If you see your engine, this is your engine, and you have in the front the air which is at very low velocity. That low velocity air is going to pass through your aircraft engine. Okay, and this air which is going to come out at very high velocity, this is coming out at very high velocity. So if you see on air, there was some force applied on air. There was some force applied in this direction, because of which it has got accelerated. Okay, so once that force has been applied, that force was applied by your engine. Okay, so now from the third law, Newton's third law, which is the action and reaction. Okay, when your air is getting some force from the engine is also going to get some force from the air, and this force is actually called as thrust. Understanding? Okay, so this is how your actually thrust is generated by your engine. Okay, so now we are going to see how you actually generate this thrust. What are the different components which are actually present inside your engine, and how we design those components. So if you see, I have also put up a diagram on explaining how the air moves through the engine. So if you see over here, we have air that is in the front, that is coming inside the engine. While passing through the engine, if you see, the engine is moving, engine is rotating, and through this the air is passing. When this air is passing, the air coming out of air will be at very high speeds. So because of that, thrust would be generated. Okay, guys, moving on. Let's take a look about what are the different components which exist inside the engine and how these components are actually designed. So if we see an aircraft engine, that is probably a jet engine. The components of a jet engine looks like this. This is a cross section of the engine component. So in engine, we have a fan that is placed in front. That fan is actually used to accelerate the air. The air that is propelled behind is used, that is accelerated by your fan. Then we have there is a Brayton cycle components. So in Brayton cycle, you might have heard about a compressor that is used to compress and increase the pressure of air. Then you have a combustor where fuel is released and fuel is supplied to the combustor, and fuel is burned and energy is released. That energy is taken up by air, and that air is going to be heated up. Its temperature is going to be increased, and once that high temperature, high pressure air, when it passes through the turbine, it is going to expand and it is going to do work. The work that is generated by turbine is used by the compressor and fan. Okay, so turbine, whatever is the work generated by turbine, 40 to 50% of that is used by your compressor, and remaining 50 to 60% is used by your fan. Okay, and once the air that is coming out of the fan, it will be moving backward, it will be moving at high velocity. Okay, this is how the actual jet engine or your aircraft engine actually generates the thrust, and these are the components which are actually present inside a aircraft engine. Okay, so now let's go into the design, into the design, detailed design, how actual design happens. Okay, so guys, if you see the aircraft engine or any of the engine that actually goes inside an aircraft, there are certain specifications which are required for that engine. Engines are actually decided by these specifications. So if you see what are the specifications which will be required for an engine. So the first and foremost, the most important specification that an aircraft engine needs is the maximum thrust that it is going to generate. Based on that thrust, your aircraft is going to move forward. So whenever any engine is fitted on an aircraft engine, the first most important criteria it has is the maximum thrust that is going to generate. Okay, so this is the most important criteria which decides your engine. Okay, once maximum thrust is decided, then we have other parameters also which actually decides the engine. Its specifications are there. So the second criteria that comes is the weight. Weight is again one of the most important criteria for engine, because aircrafts have to fly. Okay, and you cannot have very heavy engines, because as we increase the weight of the engine, the running cost of the aircraft, or the mileage of the aircraft, it reduces. Okay, so if you put 1 liter fuel into the aircraft, it probably will go a lesser distance if it has to have very heavyweight engine. So the second most important criteria is the weight. Aircraft engines should have the minimum weight as much as possible. Okay, and the last thing that is again very important is the efficiency or the specific fuel consumption. I'm sure you might be aware about the efficiency, how efficient is an aircraft. If you put up 1 liter of fuel or 1 kg of the fuel, how much is the power that is generated by the aircraft? That is again the measure of efficiency. Okay, so these are the three main criteria which are actually used by aircraft engine designers to design your aircraft engines. Okay, so once we have seen all these criteria, now let's see how does actually engines, or how does actual engines are designed. Okay, so guys, since we have to design an aircraft engines, generally whenever any new aircraft is built, let's say Boeing or Airbus, they are going to make a new aircraft. when they make a new aircraft, they have certain specifications of aircraft, like this aircraft will be a narrow body aircraft which will be used to carry passengers from, let's say, Bangalore to Delhi, or it is going to take passengers from Srinagar to Chennai. So that is one type of aircraft. These are called as narrow body aircraft. They have smaller capacity, they have smaller engines. Then there is another aircraft which is going to fly from New Delhi, and then it is going to move to, let's say, Vancouver, Canada. So New Delhi to Canada, or New Delhi to, let's say, Paris, somewhere, or inside Germany or in the Britain. These aircraft which have to carry the passenger for a very long durations, these are generally wide body aircraft which are going to travel for a larger distance. Okay, so these are the two major classes of aircraft, and for both these classes there are different types of engine that we actually have. Okay, so whenever a new engine is being designed, that is going to go on a new aircraft. Generally, the aircraft manufacturers, they decide the aircraft, and based on that aircraft, they will go and decide the thrust of the engine that needs to be there. So let's say a new aircraft, let's say Boeing A320 Neo is designed by Airbus. Now, once the A320 Neo is designed, the design is finalized by Airbus, they are going to give a specification to engine manufacturers that they need an engine which can generate, let's say, 30 kilonewton of thrust, or let's say 100 kilonewton of thrust, with weight to be less than 3 tons and with efficiency to be minimum this. Okay, so they will define the specifications for the engine manufacturers. So engine manufacturers have to design an engine with the specification that is provided by your aircraft manufacturers. Okay, so now once the engine manufacturers have specification, let's say they have to design an aircraft with a thrust of let's say 100 kilonewton. Okay, so now what engine manufacturers actually do is, the leading manufacturers in world are GE, Rolls-Royce, then we have Pratt and Whitney. These are some of the most advanced aircraft engine manufacturers. They have a large fleet, and they have a lot of engines which are there with them. So what these engine manufacturers will do, they are going to see all the engines which are present with them. Let's say if we see the class of engines that GE, General Electric has. General Electric has one of their most successful class of engines, that is CFM56. This is an engine which is fitted on a narrow body aircraft engines or the smaller duration aircraft engines. Okay, then they have another class of engine which is fitted on very large aircraft, and that is the GE90. This is another class of engine which is GE90. They also have engine that is GP7000, and they also have GE9X. They are designing a new engine that is GE9X. So they have a lot of class of engines which are available. Okay, they have very high thrust, they have smaller thrust, they have in between some medium thrust. Now they want to design a new engine. If they want to design a new engine, probably what they are going to do is they are going to see one of the similar engine which is going to be used for this thrust. Let's say if you see the CFM class, the thrust is around 80 to 90 kilonewton. Okay, and they have to design an aircraft with 100 kilonewton thrust. So what they are going to do is they are going to select one engine, that is your CFM, as the base engine. So they will choose the base engine. So whenever there is a design of new engine, none of the companies, they design altogether very fresh engine, altogether a new design. Nobody does it. What engine manufacturers actually do is they will take one of their models, one of the successful models, and then they will upgrade it. They will rescale it. So this engine is having 80 kilonewton of thrust. Now they are going to scale this engine and make it of 100 kilonewton thrust. Okay, so they will choose the base engines. Once the base engine is chosen, now they are going to optimize or they are going to rescale that engine for the requirement that you are going to have. So over here, if you see, there are two designs. There are two designs that I'm going to compare. So this is your CFM engine fleet that I was telling, and based on this CFM, GE has taken benefit of CFM, and they have also taken benefit of these large engines, and they have clubbed the benefit together, and they have come up with a new engine, which is the LEAP engine. This LEAP engine is one of the most efficient engine that has been designed till date for aircraft engines. So now, if you see the comparison of the two engines over here, on the left hand side, this is your CFM engine specification, and this is your LEAP engine specification. So if you see the comparison of specification, the base specification is the takeoff thrust. Now, if you see the takeoff thrust of CFM, that was somewhere around 106 to 95 of kilonewton. Okay, compared to that, if you see the LEAP engine thrust, that is slightly higher, that is somewhere in the range of 130 kilonewton. So that is roughly around 20% higher thrust. Okay, now if you see the other parameters are just a scale up of your CFM. Okay, so if you see the compressor of CFM engine will have one fan, then 3 LP stages and 9 HP stages. Again, if you see the compressor of LEAP engine, that has got one fan, 3 LP stages and the 10 HP stages. So since the LEAP engine has to produce little higher thrust, then it has to have some modifications. So if you see, the number of stages have gone up to 10. Okay, instead of 9 HP stages, which was there with CFM, LEAP has got 10 stages. Again, if you see the turbine, here the turbine was 1 stage HP and 4 stage LP. That design is slightly modified in case of a LEAP engine. Here we have 2 stage HPs and 7 stage LP. So it is very simple that the 1 stage of HP of your CFM is divided into 2 stages of HP. Okay, and 3 stages of or 4 stages of LP have been redesigned into the 7 stages of HP to increase the efficiency and to modify some other parameters. Okay, then if you see the length is most probably almost the same for both of these engines. If you see the fan diameter over here is around 68 inches. Over here, if you see the fan diameter, it is somewhere around 78 inches. So this model is nothing but just a scale up of what is there already into the service, which is CFM that has been scaled up to around 50 to 20%. Okay, so this is the first process that is actually done by manufacturer, and that is to choose the best engine. Okay, once they have the best engine, now they are going to go into the second stage, which is the cycle design. Cycle design is one of the most important stages. So once you have finalized your base engine, which is going to be CFM, now you are going to modify the CFM engine into the LEAP engine. Okay, so the first important thing that is going to come is the design the cycle. Okay, how your Brayton cycle is going to look like, and to design the Brayton cycle or to design the cycle, the path that is taken up by the manufacturer is the first input that these manufacturers have is the thrust. What is the minimum thrust that this engine is going to have? Once that thrust is finalized, now you go into your designing phase. So when your thrust is going to be decided, you would produce the thrust with help of your fan. So the moment your thrust is decided, you have to come up with a fan diameter so that you can produce the required amount of thrust. So the first thing that is decided is your fan diameter. Once the fan diameter is decided, now you are going to go into how much power is required to run this fan. Okay, because fan is going to be run by turbine. So then you go to the next stage, and that is design the suitable turbine. Okay, if your fan is going to require, let's say 100 kilowatt of power, so that power is provided by turbine. Turbine is going to run your fan. So ultimately, you have to design a turbine that is going to produce 100 kilowatt of power. Once that turbine is finalized, Now you go to the next important component, which is your compressor. We know that the turbine in Brayton cycle is one of the most important parameter, the most important component, and the turbine is going to be run only by the air that is supplied by your compressor. Okay, so you decide the compressor, which is going to be the next component, and once the compressor is decided, then we come up to the last thing, that is your combustor, and how much fuel is to be provided to your cycle. Okay, so we have decided the thrust. Let's say there is a thrust which is 100 kilonewton thrust is required to be generated. That would be generated by a fan. That fan is going to have, let's say, a diameter of 76 inches. Okay, that to run that fan, you need a turbine that is going to produce 100 kilowatt of power, and that 100 kilowatt of power will be produced by supplying air through the compressor that is going to consume, let's say, 40 kilowatt of power. Okay, and this 100 kilowatt of power would be generated when you are supplying the fuel or when you are supplying the heat, which is, let's say, 200 kilowatt energy that you are supplying to the combustor. Okay, once all these things are finalized, now you are going to go back to your fan. Once the cycle is finalized, guys, this is an iterative process. This is not a process that we move in the downward direction. It is not as simple as it looks, because there are thousands of parameters which changes by changing very one small parameter. The moment you change this 100 kilonewton to 101 kilonewton, all the parameters of your turbine, fan, compressor, combustor, everything is going to change. Okay, so this is an iterative process. You have finalized your fan diameter. Once that is finalized, your turbine will be finalized. Turbine is finalized. After that, compressor, after that, combustor. And once all these are finalized, your cycle is designed. And now once the cycle is designed, now again we will go back and we will try to see how much thrust is generated by your engine. If the thrust generated by engine is more than 100 kilonewton, then we are ready to go for the detailed design. Okay, but if the thrust is only, let's say, you got only 89 kilonewton of thrust, so now you are short of 2 kilonewton. So what you should do, the moment you get 98 kilonewton of thrust, now you have to increase the dimension of your fan so that you can go to 100. So then again you increase the dimensions of your fan. The moment you increase the dimension of your fan, the turbine size is going to increase. Once the turbine size increases, your compressor size increases. Once the compressor size increases, again your fuel end cycle they changes, and you have higher fuel that needs to be supplied. Okay, again you will calculate the thrust, and this goes on till the time you have the required thrust that is being generated. Okay, so once this is finalized, once your cycle is finalized, okay, you are going to have very specific dimensions which will be present, or dimensions which will be fixed. Okay, the moment your cycle is finalized, you are going to have specific dimensions to everything. Let's say you have said that there will be a 76-inch diameter fan that will be required to produce that 100 kilowatt of turbine is required. So your turbine would be delivering 100 kilowatt of power. Then your compressor should be delivering certain air at given pressure, and your fuel should be supplied like this. So after that, your cycle is freezed. Once all these parameters are finalized, your cycle would be freezed. So you have a fixed cycle. You have designed a cycle that will be your Brayton cycle. In this cycle, what you actually decide is how much amount of air is going to come inside your engine or the compressor. Okay, that compressor is going to increase its pressure from, let's say, 1 bar to 60 bar. Once that air is coming out of the compressor, it is going to go inside the combustor. There you are going to supply fuel of, let's say, 5 kg per minute, and then that air will be moving to the turbine where expansion will take place. Exhaust gases will be coming out at 500 degrees centigrade, and the thrust generated by the fan would be used to propel your aircraft. So this is how the first thing, which is the most important thing. See guys, this is the most important part of your engine design, and that is the cycle finalization. Once the cycle is finalized, now all these components, they have specific parameters to deliver. ठीक है, समझ में आ गया? Okay, so now guys, let's go into one by one component. Okay, so once the cycle is finalized, now all the single components will be designed. So let's say the first thing that needs to be designed is the fan. Okay, for the fan design, we have, what are the simple inputs that we need to have? So we said your fan would be having 76 inches of diameter. So you have one constraint which is available to you for your fan, that is your diameter should be 76 inches. Then you have cycle parameters. This cycle parameters would be taking in how much amount of air will be coming inside your fan, at what velocity it will be coming inside. When it is going out, it should go out at what velocity. Okay, then you will be provided with a torque from the turbine. Let's say 100 kilonewton meter of a torque would be provided to you. So these are the inputs that are actually given to you. You will be having some power coming in. There is a constraint on your diameter. There is a constraint on what are the different specification. And based on these, an engine or a fan designer would actually design the fan, and he is going to design the fan such that the thrust produced by the fan is equal to, that is what is required by an engine aircraft. Okay, so now if you see, this is one of the fan that is that comes on the modern aircraft engines. Okay, so if you see, this is very one of the most advanced fan you can think of. Okay, once if you see, these are the blades which are actually present on an aircraft engine fan. Okay, so when a designer is designing the fan, what are some of the key things that he designs? What are the key things that he designs? The first important thing is the number of blades. How many number of blades we are going to have? So you have certain inputs. These are the inputs which are provided to you. But what are you going to design? You are going to design what will be the number of blades. Okay. Then what will be the profile of the blade? Everywhere at each location, what will be the profile of your blade, so that the air which is coming in is accelerated properly. Okay. Once these two things are designed, the number of blades and the profile of your fan. Okay, so once these two things are designed, now the fan would go into the detailed design. It will pass through some of the design stages, because once you have designed the fan blade, okay, you have designed the number of blade and the profile. Now it will undergo stress analysis. Whether the fan, when it is going to rotate, it is going to rotate at very high stresses. The centrifugal stresses that are generated by the fan blade, whether your fan blade would be able to sustain those stresses. Okay, so then it is undergoing the stress analysis. If you do the stress analysis, you will find that there can be certain locations where the stress is beyond the allowable limit. So what you do? We change our design, we change our profile, we change the mass of the blade. We might also change the number of blades. So if you see, this is iterative process. Let's say you have decided with 18 number of blades and very specific profile. But with these 18 number of blades, the thrust you have generated, but your blades are failing. So the moment you went to these blades, your stress analysis says that these blades are going to fail. Every blade has got higher mass. So then you go and change the number of blades to 20. Once the blade number is changed, which is 20, altogether a new design is going to come up, because whatever the blade profile that you generated, that is not going to be applicable for 20. So you design the blade profile again. So for these 20, you design the blade profile again. You again run the stress analysis, and now you find out that the stress is within your limits. So now you are going to have 20 blades. So there are many analyses which are done similar to this, and once your blade passes through all these analyses, then only your final design would be considered to be the last. Is it clear? Okay. Okay, so this is a brief about how the fan is actually designed. Now let's go to the next component, which is your turbine. So a turbine designer, when he's going to design his turbine, he is going to have many inputs. So if you see what are the inputs that are required, so the first input would be the hot gases specification. So what is the pressure, what is the temperature, what is the amount of air that is going to go inside the turbine. So your air is going to come up at 54 bars, it is having 1300 degrees centigrade, and then it will be moving, or it will be having a mass flow rate of 100 kg per second. These specifications a turbine designer would have with him. Okay, and he will also have compressor and fan data, because you have to run the fan. So you also have a constraint in mind that you need to generate sufficient power such that you can propel your compressor. You can also propel your fan. So generally, when we consider the fan and your compressor data, generally we decide the speed at which these two devices run, because your fan is designed for one particular speed, your compressor is designed for one particular speed. So your turbine should be able to provide the power at that particular speed. So you have to design your turbine for that speed. So once you have these all data with you, now you are going to design the turbine, and that turbine as an output will have certain specification, like what are the number of stages which are present inside the turbine, what will be the size of the what will be the size of your turbine, and how does the profile actually looks like, what are the different other parameters your turbine is going to have. So if I give you a brief idea, this is one of the turbine stages. Okay, so if you see over here, this is one stage over here, and then the second stage over here. This is one stage, this is your second stage, this is your third stage. So when we are designing the turbine, what are actually we designing? We are actually designing the profile. Okay, how does the profile of your stage look like? Because profile is the one thing that is going to generate the power. Okay, then we are going to decide how many number of blades are there in each stage. Okay, so if you see, these are the blades that are there. Then what will be the other parameters, like the height of the blade, the material of the blade, and other. There are a lot of parameters, like how the cooling of the blade will take place, how the heat transfer will be happening, how the air would be moving. All these parameters, they will be decided by the turbine designer. Okay, once you have designed the turbine, now you will see whether the turbine that is designed by you, if they are provided with these specifications, are they going to produce the same thrust or same power that is required by compressor and fan at the given speed. Okay, so once that is decided, your turbine is finalized. Okay, when your turbine is finalized, now we will go to the next component, which is your compressor design. If you see, all these things are going in parallel. So a fan designer would have input from the cycle, a turbine designer would have input from the cycle, a compressor designer would have input from the cycle, a combustor designer also have input from the cycle, and they all are designing parallelly. Okay, so the compressor design, on the compressor you have the cycle data. So for the compressor, the required cycle data is what is the amount of air that is going to go inside, and what is the pressure increase that it has to achieve. Okay, so compressor has to develop a pressure of, let's say, 60 bar. So to develop that pressure, what should be the design of your air compressor? Okay, so based on that, if you will see the aircraft compressor, they look like this. The aircraft engine compressors, they have multiple stages. So I have already told you like the LEAP engine had 3 plus 10. Okay, 3 LP stages and the 10 HP stages. Based on these, now your compressor is designed. Okay, and each stage would have its specification, like what will be the material of your blade, what will be the height of your compressor blade, what will be the profile of your compressor blade, what will be the different stresses that will be coming up, how the heat transfer will be happening. All these things are taken care by all the component designers. Yes, they use lot of softwares for iterations. These simulations are actually done on the advanced softwares that generally these companies have. Okay, they have software for all the analysis, like heat transfer analysis. They have software, stress analysis. Most of the stress analysis nowadays is done in ANSYS. Okay, and there are other softwares also, like cycle softwares. Cycle softwares are their in-house build tools. We don't have generally the readily available, because all the companies, they have different designs, and based on those designs they develop some softwares which will be generally designing the cycle. Okay, also for fan there are going to be a lot of softwares. Fan will be having stress analysis as well. Fan will undergo vibration analysis as well. Fan will undergo if blade liberation simulations. If there is a crack in blade, that blade gets liberated, and what will be the impact of liberation of that blade on the engine, that is also going to be seen, or that is also going to be analyzed by the engine designers. Okay, so there are lot of things which actually go into the design. Okay, so similarly we go to the last component, which is the combustor. Once you have finalized the amount of air that is coming inside the compressor, that is going to go inside the combustor, now you decide how much fuel is going to go inside your combustor. Once you have fuel that is going in, you have air that is going in. Now you have to design a combustor such that the energy is released by the fuel, and the air that is coming inside will be having that energy, and its temperature increases. So based on these inputs, your combustor will be designed. Combustor design is one of the most difficult designs that we actually see. Okay, if you see the combustor generally actually looks like this. This is one of the most advanced combustor that is installed in the LEAP engine. Okay, that I have actually shown you. This is the TAPS combustor, twin annual premix swirler. Okay, so this is what is the combustor actually looks like. Fuel comes from here and the air comes from here. Both of these are burned inside this combustor. Now if you see, the combustion process is happening. That combustion process, if you see, generates very high temperatures, and due to these high temperatures, the liner which is present over there, if you see, this is the combustor wall that we actually see. This is the wall of the combustor. So they are going to see very high temperatures, and at these extreme temperatures, the combustor material that might fail. Okay, so this is one of the most typical design, like most extreme conditions under which the combustor is designed. Okay, so a combustor engineer would take into account everything, all these temperatures, how the heat is being released, and how your component is not going to fail. Okay, once that these components are designed, now you have air that will be coming out at certain temperatures. Okay, so you have your air that is coming out at 50 bar and 1300 degrees centigrade, as expected from you by as given by your cycle. Okay, so we said that the turbine is going to have air coming at 54 bar and 1300 degrees centigrade. Whether you can provide those conditions. Okay, if you are not able to meet these conditions like 54 bar and 1300 degrees centigrade, let's say the temperature that the air is having is only 1278 degrees centigrade, then you have to redesign your combustor so that it reaches these conditions. Because if you don't have these conditions, your turbine is not going to generate the power that is required by your fan. If turbine is not going to generate it, your fan is not going to generate thrust, and if the thrust is not generated, your aircraft is not going to move at the speed at which it is required. And if You decided that you will be starting from Delhi at 1 o'clock, you will be reaching Bangalore by 4 o'clock, then 4 o'clock you will not be able to reach, you will reach at 5 o'clock. Okay, so the thrust generated by your aircraft will be less, or engine will be less, and your aircraft will be moving at a lower speed. It might also happen that your aircraft might not even take off. If the thrust is not generated properly, it might not even take off. ठीक है? Okay, chalo. Okay, so guys, once these all things are designed, so once we have designed our different component, so if you see, we have designed the fan, we have designed the turbine, we have designed the compressor, we have designed the combustor, we have designed all these components. Once all these components are designed, now theoretically everything has been designed, but still your engine is not competent enough to be supplied to aircraft manufacturers. So there is going to come a very important stage, and that is the testing of engines. Okay, so we are going to test the engines in real life. We will make the engine. So if you see, this is a test rig which is built for an engine testing. Okay, so we make many engines, like 20 to 30 engines are made. Those engines will be used for testing. Okay, so you have an engine which is installed on a test rig, and now your engine would be run. If your engine is run, now you are going to supply the fuel to the engine as if it is installed on your aircraft, and now you are going to run it through your cycle. If you see the engine, when you run, you will be having certain parameters on which that engine will be running, and now your engine is going to produce thrust. That thrust is measured by the test rig, and if that thrust is 100 kilonewton, then your engine has met one of the criteria, that it produces the required amount of thrust. Okay, understanding? So guys, if I will give you certain numbers, okay, of how many tests are actually carried out on these engines. Okay, you will be very surprised to know that does it really take place. Okay, so this is how the testing of engines actually take place. Okay, if I give you the numbers of hours or the tests which are actually done on these engines, you will be surprised to know that some of these engines which are like, generally when we have these engines, generally the engines would be having names like FETT. FETT is nothing but first engine to test. This is the first engine that has been manufactured and it has been put on test. Then you have SATT, which is second engine to test, third engine to test. Okay, so these are the engines which are actually made to test some of the conditions, and you will be surprised to know that these engines are run as if they are actually installed on an aircraft, and they might be run for very large number of times. So let's say one your aircraft engine which you are designing is going to run from India to Paris, and that flight is going to take 8 hours. So this engine would be run at those same conditions for 8 hours. Once it is run for those 8 hours, it is going to run continuously on that test bed for 8 hours. Then your one cycle is complete. And this engine would be run for such 5,000 cycles, let's say. So every day it will be running 8 hours, or like twice, thrice in a day. It will be running continuously for 8 hours, and you will be surprised to know that these engines might even run for 20,000 hours, 30,000 hours. And these engines which we are running, which we are testing, they are actually test, let's say for 5 years, it is in testing. Continuously for 5 years, this engine is running. The second engine is running for 3 years, undergoing different cycles. Let's say this engine is going, or this aircraft is going to take off from India, and this is going to go to Canada. While going to Canada, if the temperatures in Canada are going to be very low. So if it is going to enter the atmosphere of Canada, there the temperatures are going to be very low. So there might be conditions where the temperatures might be low, like in the normal condition, minus 50 degrees centigrade. Okay, so this engine will be made to run at minus 50 degrees centigrade also. There might happen that this engine sees some ice formation in the clouds. Okay, and it will also be fed up. It will also be fed up with ice cubes, and those the air that is containing the very small ice particles that will be going through the engine, and whether that engine sustains it or not, that will also be done. There will be a bird strike test on this engine. There will be a live bird, sort of a live bird, which will be thrown inside the engine, and it will be seen whether this engine sustains that bird flight or not, it bird strike or not. Okay, there will be one test which is also done for the fan blade liberation. So you have a fan blade. So I have shown you the fan blade. Okay, so this is the fan blade. There is one specific requirement by FAA, the authorizing authority in USA. So they have one specific test. What you generally do is we release one of the blades from here. While the engine is running at 4,000 full speed RPM, you release one of the blades. How do we release it? We actually put some explosive over here and we trigger that explosive. That explosive makes the blade crack, and once that blade is released, now it will be seen whether your engine, the engine cowl which is there, which is present over here, this outside engine cowl which is present, whether that cowl can capture the blade. The blade should not go out of the engine. Why? Because if let's assume that you are sitting in your aircraft. Okay, you are sitting over here. Let's say let me give you a very interesting scenario. Okay, let's say you have your aircraft, you are sitting over here. Okay, you are flying in this aircraft. Let's say you were sitting over here in Airbus A380. There was one blade released from here. This released blade can go and pierce the nacelle of the aircraft. When that blade is released, it is going to strike. It can go and strike the aircraft over here. And if that happens, your aircraft is going to fail and this whole aircraft is going to go down. So there is very specific requirement that the blade that is released, if while your engine is running and if the blade is released, your engine should be designed such that it can contain that blade. That blade should not go and strike the nacelle of the aircraft or the fuselage that we actually see. If that is happening, then only your engine would be certified. So in actual condition, the engines that we are going to test, this engine would be shredded. The engine in which you are going to actually see the fan blade release test, that is going to go like chithade chithade ud jayenge uske. Okay. So this is one of the again tests. So under these conditions, all the extreme conditions, your engine would be tested. And if everything is fine, if everything is good, then only your design would be certified by your FAA. Okay, once that is certified, now your engine can go into the production and now it can be handed over to the aircraft manufacturers. If you are running your aircraft engine and if you find that the thrust that is generated is less than 100 kilonewton, let's say your engine was supposed to generate 1000 kilonewton, but on the test bed it is not generating 1000 kilonewton, then you have to redesign your engine. Again, the process starts from the designing of the fan. So if this thrust is not generated, you have to go for 77 inches fan. And if you have to go for 77 inches fan, again, everything is going to change. Okay, mass flow rate is going to change. Then the fan diameter, it has changed. So its profile will change. Once the profile changes, the mass of the fan blade increases. Again, you have to go for the stress analysis. Once the stress analysis is okay, then you go for other analysis. You will again go on this engine for the fan blade test that release. Okay, if let's say the thrust is generated, that is okay, 100 kilonewton, but the efficiency is not good. So we have said that there are three main parameters which are actually used in the design of an aircraft and aircraft engine, that is the thrust, then weight, and then efficiency. All the three criteria should be met, then only your engine would be installed on an aircraft. If the weight is larger, you have to reduce the weight. If the efficiency is less, you have to improve the efficiency. And for all these, all iterations will again take place. All the iteration. Your turbine is going to be redesigned, compressor is going to be redesigned, combustor is going to be redesigned, fan altogether redesigned. Again, all the components, they can be scaled up, scaled down. Okay, so this is how an actual engine is designed. I'm sure, guys, you must have got some idea on how the engine is designed. Is it clear to everyone? Now I can take some of your questions which you have asked. So, guys, our lecture is over now. If anyone of you have any doubt, you can post it in the comment box. I can reply to you. Those students, those who are going to watch it offline, you guys can put it in comment box, and I will always try to reply. Okay, guys, never forget to like this video and subscribe to channel for more such interesting sessions. Okay. So, Amrit, you are saying very dangerous work. Yes, it's really dangerous. So, testing of these engines is really dangerous. If you might have heard Elon Musk, okay? Elon Musk, SpaceX is in this phase. They are testing some of their vehicles. So you might have seen that a lot of vehicles, they are failing on the test bed. Okay, that is what is actual thing that happens while we are actually testing these engines. There are many failures, and once those failures occur, we redesign our aircraft engines, and then only we put these engines into the service. After undergoing so many of tests, then only your engines are certified, then only your aircrafts are certified, and because of this reason only, the number of accidents that you see in your aircraft engines or in your aircrafts, they are very, very, very small. As compared to all the other modes of transport, aircrafts are the most safest modes of transport. Selvam, you are saying which type reaction we use in aircraft. What do you mean by reaction? Sir, iron thruster का कहने okay, iron thruster is the next future technology that is being developed, and that is developed for space applications. Okay, composite materials. Okay. Okay, Amrit, you are saying Paras Defense join kar lo. Okay, I will think about it. That's a good idea. Okay, so guys, I'm sure you might have got some idea about how the aircraft engines are designed. अगर वीडियो अच्छा लगा है तो गाइस लाइक कर दो, शेयर कर दो, अपने दोस्तों को जरूर बताओ, because this is the video which I purposefully made for those students, those who have interest in aerospace, and they want to learn how the actual engines are designed. Okay, so if that is all, guys, let's finish this lecture and see you with some of the more interesting videos like this. I hope you liked it. If you liked it, hit this button, and you can also put in the comment box what are the future videos that you, or future topics on which you want the videos to be made. I will try to make videos on that. Okay, so that's all, guys, what we have for today. Thanks.